Okay, 5A, 2013. Right, what is superposition of waves? When, well, maybe someone can tell me before I write it down. Superposition of waves? No? No? Cal, do you want to try? Superposition of waves? How would you describe that?
When the maximum and minimums are in the same point, are the same.
Not quite. You want to try? No, that's something else. That's
When two waves are combined,
yeah.
make a new one.
At any given time, the combine of two waves.
Yes.
Is the sum of.
We nearly have it.
Who wanted to hear the principle superposition?
Yeah.
When the two waves combine, the total wave will be the algebraic sum of two.
That's it. Yes, that's the one. When two waves combine, the new wave produced is the algebraic sum of the two. Something along those lines. Really, I'm looking for the key word in blue there, algebraic sum. Did you have a meeting with Emer?
Yeah.
You in lots of trouble now? Almost out of trouble. And what about Ronnie? You all were in a meeting with Emer? And you're all in trouble?
Yeah, that's good.
That's good. Here. You truly don't look too happy.
It was nice knowing you.
Yeah. Yeah, well, everybody take one last look at Joshua and his friends, and you won't be seeing them anymore. Alright. So Joshua and Company, we are on page 15. Yeah. It actually would be a good name for a band, I think. Joshua and Company. Alright, that's part A done. Now on to part B. Two light waves being used to show interference effects meet at a point, and this results in destructive interference. Explain what you mean for destructive interference. So, for destructive interference, what do you need? Well, firstly, the amplitudes must be the same. Anything else?
The crest meets the trough.
That's one of them, yes. Now, what you said there, Tanish, the crest must meet the trough, or the maximus meets the min. There's a special word, or special collection of words that describe that. No. There's a special expression for when the max meets the min and the min meets the max in the two waves. Not quite that one now. Not for that. It's like that.
Destructive interference. Oh, that's what.
That's what we're defining. We say out of phase. Fully out of phase. That means what everybody is saying. The max and the min happen together. And there's one more thing really as well, but we kind of have it automatically or anyways from the out of phase, but I'll write it down. And they should be the same frequency.
Steven, are you writing down all the answers, or is that okay if I choose one of it?
No, you should write this down. Yeah. What word means same frequency?
Coherence.
Yes, coherence, yeah. Coherent source. actually, I think that's really, we can mark that off as the answer to the next part really. So I'll just call that now B part 2.
all be 2.3.
Okay. So part 2 is why must the two lights come from the same source? Well, if two lights come from the same source, we say then that they are coherent, meaning they have the same frequency and they have the I think that's actually enough just to say frequency. It's 2 marks as well, so I feel like I should be saying something else too.
Diffraction.
Huh?
Is that diffraction?
You already have
No.
phase that's coherent source.
Yeah.
So like 1 each.
In practice, the 2 light rays will come from a single source of light. Why is this necessary? Well, I think that is enough actually. The main reason is coherent source means they have the same frequency.
I didn't get the question.
Yeah, they basically say when you do these experiments with the light, you use the same source and then you split the light. And you might say, well, why don't you just have lots of little sources, yeah. And the reason is, well, if you have one source, you can make it the same frequency. And also you can make, if you split it, you could make it the same amplitude, you know. And I'm curious, do you have the answer there? Soon.
Yes.
What did they go for?
Which part?
B part 2.
Lightweight, masculine, and
Okay, so they actually put same thing, just coherent was enough to get to the 2 marks. Okay, let's look at part C now. Now part C is now we have some calculations. So we have Young's double slit, we have our frequency, 4.77 times 10 to the 14, and that's a 14, sorry, 14. And we have our light, and then it passes through a narrow slit, and then passes through 2 narrow slits. So we have our, basically our diffraction grating here. Okay, and then there's the wall. And it makes a dot in the center, as you know, and then a smaller dot here and here, and then a smaller dot here and here. This is N0, N1, N2. And a screen is placed 1.55 meters from the double slit. So they're saying here to here is 1.55 meters. That is in the formula. It's the D, yeah. What else are we told?
20
That the 20 fringes is 8.5 millimeter apart.
Is that divided by 19? Or?
Yeah, but in the marking scheme they divide by 20. I'm sorry, I was supposed to look that up online. We'll just do what they did in the marking scheme and divide by 20, okay? So the distance between these is 80.5 times 10 to the minus 3 divided by 20. That's the distance between these dots.
Is X.
It's the X. So we have our formula, don't we? What's our formula? It is lambda, what is it? FD over something, I forgot now what it is.
X over D.
FF over D, that was it, yeah. Hold on, guys. X is the fringe slit to screen distance. Okay, so here we have lambda. Well, hey, before I go on, if you just look at this, do we know the X?
Do they have an X? Yeah, or lambda.
Yeah, no, I'm just trying to formula. Do we know the X?
Yeah.
We do. Do we know this?
Yeah.
We do. This is the slit separation. That's the distances here. We don't know that. Do we know the lambda? No, but we can easily get it from using the frequency because you have the formula C equals F lambda. So you can easily get out lambda from this formula and this. So let's do that first.
But that's for different things.
Huh?
The first question is the station of the double slit.
Oh yeah, so that's the s. So before I get the s, I have to get the lambda. 3 times 10 to the power of 8 divided by 4.77 times 10 to the 14. I get 6.289 times 10 to the minus 7. Okay, so now I know the lambda, now I know the x, now I know the d, so I can find the s, no problem. S is lambda multiply d over x, which equals lambda multiply 1.55 divided by x, which is 80.5 millimeters divided by 20. So I hope I typed that in all right. I got 2.42 times 10 to the minus 4 meters as the answer.
2.42.
Yeah.
That's 10 to the minus 4.
Huh?
That's 10 to the minus 4, you said?
Yeah. Now, what I really like about this question is, firstly, that part is easy, and then, if that wasn't easy enough for you, they ask you to do the same thing again, just with a different number of 1.25. Where's my pen gone? Here it is. So we do the same thing again, except instead of the 1.55, we put in 1.25. So I need to retype everything in again. 6.289 times 10 to the power of minus 7 times 1.25, sorry, 1.25. All over...
That's the question.
Yeah.
1.95.
What, 1.95? So, how many marks do you get? Believe it or not, you get 6 marks for using that formula with the XSD lambda in it.
Do what happens in the formula?
And you have it in the formula book. So, what's the problem? I don't understand what the problem is.
In the formula, x
X is the distance between the lines.
1.55.
No, that's the D.
Yeah.
Yeah. Yes?
It is not the end, it asks for the spacing between edges and the...
Yeah. Which is it's just a way to try and trick you, that's all. So if you look here, imagine this is my paper here, I don't know, and you have your bright light here, and then you have your other bright light here, and then it's dark here. I think in the first example we were getting this distance, and in the second one we wanted to get the distance between the dark areas, which in fact is the same thing as the... I mean, if we only have one formula, it's going to be the same thing. And I'm sure that's the answer in the book. Is that the answer?
The first question has
So,
to do...
the second question you have to find x now.
Yeah.
Oh, sorry! You're telling me something different. I'm so sorry. Yeah, I did it. I got the wrong thing. What did they want?
No, you're right. It's just that you need to add second part to find x.
If the distance between the slits were 1.25, determine the spacing, the x. Did I not get the x?
You got the x.
Last. Sorry. Rats. I was using this formula, but I should have rearranged it. X equals lambda d over s. Yes?
Yeah.
Okay, now let's type my numbers back in. So I knew what I was getting, but I was using the wrong formula. Lambda 6.289 times 10 to the power of minus 7 times 1.25 all over 80.5 times 10 to the minus 3. Okay, so is it... Wait, it's the same answer. 1.95?
No.
No? Am I typing it in wrong?
The D is changed.
Hang on.
D is 1.5.
Hang on. Stay focused. that, and then the D is 1.25, yes, and what's the F? It is 2.42 times 10 to the minus 4. Success. 3.25
Yes, and
No.
then to the minus 3.
times 10 to the minus 3, yeah?
2.46.
I got this on my calculator. What's the answer in the book? Is it this? Yeah, okay. 3.25 millimeters.
What did you check this?
Yeah, I should write it down, shouldn't I? I typed in the 6.289 times 10 to the minus 7 times 1.25 all over 2.42 times 10 to the minus 4. Yeah, same. Okay, can I go down? Right. See, that's what I get for being cocky and going, well, this is easy, and there's 6 marks, so I shouldn't have been so cocky there. It's how the exam got its revenge on me. Okay, part 3 now. If the light is replaced by white light, describe what happens basically to the dots. Okay, so, as I'm sure you know from middle school, white light is white because it's made up of all the colours that we can see. So we have, of course, white is really a red light, green and blue all together. And we also know from middle school that the way to get all these colours is you have white light and you split the white light using a prism. I mean, this is middle school science knowledge really, I'm not telling you anything new. And they want to know what would happen if you put this light through the diffraction grating. So the first thing we need to remember is, let's just write it down, red, I'll just put 3 down, red, green, red, yellow, green, blue, indigo, violet, so red, green, blue. Which one has the highest frequency?
Red.
Red. And which has the lowest is the blue. So here is high frequency and then here is low frequency. Now if I look at my formula, the one that tells me the distance here, the n lambda equals d sine theta, it gives me the distance here. This formula. In this formula, it doesn't give me the distance, sorry, what am I saying? It gives me the theta. In this formula it gives me the theta. So I'll just rewrite as sine theta equals n lambda over d. So let's just look at the first dot as an example. So that means n is 1. So I get sine theta equals lambda over d. What?
Isn't frequency of 2 is higher than here? Because wavelength...
Oh, sorry, you're right. You told me, yeah, it's the wrong... red...
Wavelength...
No, red, hang on, don't confuse me. Red, orange, yellow, green, blue, indigo, violet. Violet is the one with the... Yeah, violet is the one... The blue is the one with the most frequency.
Yeah.
Thank you for pointing that out. So this one is the high one, and this one is the low one, for frequency. Now, remember, we need the picture, yes?
So we were more than blue.
Yeah, that's it. So, for wavelength, which one has the biggest wavelength?
Red.
Red has the biggest wavelength, and then which has the smaller wavelength?
Blue.
The blue has the smaller wavelength. Okay? So, here the d is the distance on the gaps, so we can't really change that. But what happens if I make the wavelength bigger? What happens to sine theta? It gets bigger.
Yes.
So therefore what happens to theta?
Bigger.
It gets bigger. So as you increase the wavelength, we get a bigger angle. Which has the biggest wavelength? It's the one with the smallest frequency, which is the red. So if you look here, red is small frequency but big lambda. So that means the angle is big. So if I was to draw this now, the red one would have a bigger angle than the other ones. the one with the smallest wavelength, did I have it around? The one with the smallest wavelength, yeah, the blue will be the smallest angle. In other words, when you look at the dots, what it would look like is, instead of one colour, you'd have red up the top, and then there'd be like, oops, that's not green, green in the middle, and then green in the middle, and then blue towards the end. So in other words, the side nearest the centre will be blue, and the side furthest from the centre will be red. So the edge of the fringe nearest to the centre will be blue, and then of course the edge furthest from the centre will be red in colour. That is, I think the answer is something like the edge nearest to the centre will be bluish, roughly blue. What's the answer there? And red furthest away from centre, yeah. So I haven't guessed. Yes, it's physics time, isn't it? Yes?
Why can't I use violet instead of?
Why can't you use what?
Because it's violet instead of blue.
If you use violet, I'll still give you the marks, okay? I'm not going to start saying violet, no, that's totally not like blue. Yes, use violet if you like. I think the person writing this exam doesn't really expect maybe people to know violet. Yes, pretty much. Okay, so I really, to get the full mark, I should really say the edge of the fringe near to the centre will be blue, and furthest from the centre, or farthest from the centre, the centre will be red-ish. Okay, next part now, part D already. So we've gotten most of it done. Okay, can I scroll down now to D? So D, two loudspeakers are connected to the same frequency source and positioned at opposite ends of a room. They each have a sound rate of 200 Hertz. So what you have here is you have a speaker here, and it's making a wave sound, and here's a speaker, and it's making a sound. And they say, as the person walks from here to the other end of the room, the sound gets louder, and then quieter, and then louder and quieter. Now you might think this is a bit strange. You might think something like, here should be really loud, and here should be really loud, and then in the middle maybe it gets quieter as you're further away. But no, what they're saying happens in this situation is it gets quiet, then loud, then quiet, then loud again. And the reason for that is what has happened is there is a stand-in wave between the two speakers. Like that. Now you saw the video of the stand-in wave. The stand-in wave is moving up and down. So first it's like this, and then it will flip like this. Yes?
Is this sound is the longitudinal wave, then how?
Yes, no, I know. So I'm just drawing it this way, but it is not visually like this. And I do not have 3D graphics to try and show you the standing wave, the proper way. But for all these problems with standing waves, it's suitable and acceptable to draw them in this form. What was I saying? Yeah, okay, so we have the standing wave. Now, they tell us the frequency is 200 Hertz, and they also tell us the distance between the loudest sounds. Now, where would the loudest happen? At these points? Or at these points? At the nodes or the antinodes?
Antinodes.
At the antinodes. as well as the loudest. And the question says the distance between the loudest, but no, hang on, that would be here as well. So the distance between the loudest is 0.85.
2 times.
Yeah, so if you wanted the wavelength would be 2 times this. 1.7? Yeah?
Wait, 2.
You know, it's so funny, because last time I did this one, Ray asked me that, and you said the reason to him, and now...
Carlos answered.
No, you wasn't asking me that class.
That's not the exact last time. A week ago, so.
Yeah.
Oh.
Yeah, no, like 2 weeks ago.
Oh, yeah.
Now, do you remember the reason why? You remember, I came up to you and I told you this in one of your classes. In ICT. Why do I remember this? We did this in class, you didn't know, he said why, and then I felt bad afterwards because I felt like I didn't get a full answer. So then in ICT, I wrote down the explanation, and he said, oh yeah, that makes sense.
Can you please just say why?
It was... Yeah, no, I guess I just dreamt that whole series of events. The reason is, if you look at the standing wave, here is one full wavelength. But what you are hearing is, or what you're measuring is the distance from here to here, which is like the distance from the max to the min of the original. So that's why we double it. Because, yeah. Now you need to picture it as one wave that's flipping up and down.
Okay, when the device was for? In which case?
That's the sound with the pipe vibrating. So the pipe vibration one, a quarter of the wave.
Okay.
Yeah, it really worries your teacher when you forget things like this. Okay, so we have the wavelength. Oh no, that's actually the part 2. Part 1 is explain why. So the reason why is because it's a standing wave. Okay, and then part 3, what is the velocity? So what's the formula for velocity? F lambda. Do you know F?
Yeah.
Do you know lambda?
Yeah.
Can you multiply 2 numbers? No, but you have a calculator which can. So we get 340. Done.